All right, we are beginning a new unit today. It's thermodynamics. Thermodynamics is the study of energy associated with heat, and we'll get into some terms later. So the first thing we're going to talk about is the kinetic model. When we talk about gases or heat transfer between substances, it's very difficult to picture what's going on at a molecular level, especially if we're going to be 100% accurate with what's going on. There are a lot of intermolecular forces. Things are different sizes. They're bound up. So we're doing this kinetic model, which is a little bit of a simplification of what's happening inside of substances, but it's a simplification that makes a lot of sense, and it makes the visualization a lot easier. So let's keep that in mind. Now, so just to summarize that, the kinetic model is a simplification of matter that lets us easily describe and understand the interactions among the particles in a substance. Just keep in mind that this is a simplification. And I'll talk about the particulars of it that make it a simplification. So, there are a couple of assumptions of the kinetic model, or 4 big pieces, however you want to look at it. The first one being the number of particles in a substance is very large. And the distance separating them is big, very, very big, compared to the size of the molecule. So let's talk about that just a little bit. This isn't so much of an assumption as this actually happens inside of matter, and we need to keep it in mind. All matter, even solids, is made up of mostly empty space. And the particles in there are very small compared to the space that's separating them. And there are a lot of particles in there. If you guys remember back to chemistry with Avogadro's number, there are 10 to the 24th particles in a mole. Atoms are really small. Matter is full of atoms that are really small. They don't take up that much space by size, but they're spread out a lot. Second assumption. Molecules in a substance move randomly. They have different speeds, they have different directions, they move in a random pattern. They're not all doing the same thing, they don't all have the same speed, it's all spread out, it's all random. And 3, the molecules interact with each other and the walls of their container in elastic collisions. So they bounce around. One thing that's important about this is that we're going to assume that the only forces they experience are forces through these collisions. We're not going to worry about intermolecular forces, so we don't have sticky molecules. We don't have anything like that. We have molecules that are bouncing around elastically with no energy loss, as if they were perfectly hard little spheres. Number 4, molecules obey Newton's laws. So when they collide with each other, when they interact, when they bump up against the wall, all the force stuff that we know and love from last year is still true. Now, this has a couple implications, and we will talk through those as we go on. So here's how I would talk about this. The molecules in a substance act like perfectly hard spheres, bouncing around with random speeds and transferring energy through collisions without losing any energy. That's what's going on. So if we are going to look at a substance and assume the kinetic model, it's a bunch of little spheres bouncing around a lot, passing energy from one to the other. And they're not going to lose any energy, they're just going to pass it around the room. So I'd like to talk about energy and temperature in terms of the kinetic model. So looking very small at an individual molecule, Each particle is moving, so each particle has kinetic energy. Now, this energy can go from one particle to another in a collision. This energy is transferred between particles through collisions. And no energy is lost in those collisions. That has an implication. Each thing has a different velocity, so each thing has a different kinetic energy. That's all right. Because these are elastic collisions, because there's no energy loss in these collisions, the total of all of this kinetic energy stays the same. And we call the total of all of this kinetic energy thermal energy. So total kinetic energy of all of the particles in a substance is the thermal energy associated with that particle. As long as it's not touching something else, as long as it's isolated, I can't change the thermal energy of an object. It's always going to be the same. Individual particles can lose and gain energy through collisions, but again, the total energy has to remain constant, has to remain the same. Now, once I put this object and touch it to something else, we can lose some of that thermal energy, and we'll talk about what that means, but for now, as long as we're isolated, that's not going to change. Temperature is a measure of the average energy per particle. Temperature is an average. Thermal energy is a total. Oh, sorry. We'll talk about that a little more. One thing I want you to think about for tonight, I'll highlight that because it popped up. One thing I want you to think about for tonight I want you to define pressure in terms of the kinetic energy or the kinetic model. So define pressure in terms of the kinetic model and think about what factors will increase the pressure. What can I do to increase the pressure? This will be on your little quiz that goes along with this, but we'll talk about these two in class tomorrow. Define pressure in terms of the kinetic model. What factors increase pressure? All right. Now, just to talk about this average thing and the fact that everything's moving randomly, we're going to look at a distribution. This is going to be a distribution of velocities. We're going to see how velocity is spread out through all the particles in the substance. This particular distribution is called a Maxwell distribution after James Clerk Maxwell, very famous in physics circles, Scottish mathematician. He's a good guy. So, we're going to look at a graph, and on the y-axis we've got number of particles, and on the x-axis we have velocity. And so here's my curve. This is a sample of a substance at 300 Kelvin. And we'll talk about temperature a little bit more later, but not right now. This sample is at 300 Kelvin. But since these particles move randomly, I have a different number of particles with a different speed. So as we move out along the x-axis, as we move this way, the velocity increases. And as we move this way, the number of particles at that particular velocity increase. So if we look right here, I could say that the most particles are moving with that speed. And down here, I have fewer particles moving at that speed. Over on this end, very few particles are moving super slow. But way over here, I could also say that very few particles are moving super fast. Now, this is my sample at 300 Kelvin. If we were to look at a warmer sample, a sample with a higher temperature, it would look like that. So let's say this is the sample at 600 Kelvin. I have a greater temperature, which means I have a greater average kinetic energy per particle, which means the average particle is moving faster. Which also means I have more particles moving faster. Now let's say this is the same sample and I have the same number of molecules. We'll talk about what that means in a second. And then let's look at a cooler sample of gas. This is the same sample, but now we're at 150 Kelvin. So, let's talk about what this graph really means. Just to keep in mind, all three lines show the same substance, the same sample, at different temperatures. So the first thing to keep in mind, the total number of particles is the same for each curve. The blue one, the black one, and the red one all have the same total number of particles. So, same total number of particles means the same area under each graph. What this graph shows me is that, say, right here, at that temperature, I have a certain number of particles. I misspoke. At that speed, I have a certain number of particles. So if I were to take each different velocity and add up the number of particles under each velocity, that would represent the area under that curve. That's what I mean by the area under that graph is the same. So since each of these graphs represents the same number of particles, all of their areas have to be the same. That's why when we heated it up, it flattened out. So even though it covers more possibilities for velocities, have less particles at each velocity because it's moving, because I still have to have the same number of particles. When we have an object at a higher temperature, I've got more particles moving with a greater speed. More particles have a higher speed when we're at a higher temperature. That's why this red graph has moved out a little bit. It has a higher temperature. So if you look at those particles, more particles here on this part of the graph, those particles have a greater temperature. Those particles have a greater speed because they have a greater, that whole thing has a greater average kinetic energy. And then at a lower temperature, I have less particles with high speed. So at my lower temperature, looking right here, I have more particles that are not going fast as particles that are in that direction. I misspelled that, but average speed, if we want to see where average speed is on these graphs, it's just to the right of the peak. So I'm going to draw that in real quick. I got an average speed here, an average speed there, an average speed there. So having a higher average speed means I have a higher average temperature. Also means I have a higher average kinetic energy. So what that means is I have a greater likelihood that an individual particle is moving faster. So something that's hot doesn't have all the particles moving faster than something that's cold.
Hi, Wes.
Hi there. It means more particles are moving faster. Not all of the particles are moving faster. Each one of those graphs has particles moving very slow. Each one of those graphs has particles down here. It's just that the average for the hotter graph has particles moving faster on average. They don't all move faster. It just moves faster on average. Just to look at what's going on with the numbers on this graph, that's where my average velocity is. Just a little bit to the right of that peak. Because we tend to trail off over here, whereas we just come up from right here. That's why the average velocity is pulled a little bit away from the peak. That's good to know. It's also good to know that within that range of those red things, we've got 99% of all the molecules in our substance. 99% of all of the molecules have a velocity within this range. Oh, sorry about that. Okay. And so very few particles are moving really slow, and very few particles are moving really, really, really fast. That's all we got for now.